This video is going to briefly describe one of the other aspects of blackbody radiation. Planck derived this distribution while other people were able to derive various other relationships that had already been empirically known and actually predict exactly the behavior of the system. So one example would be Wiens Displacement Law, which says that this Planck distribution curve has a maximum at a particular wavelength. Well, a spectroscopist named Wien had already discovered that law, and the blackbody radiation, when you actually take the derivative of this function, set it to 0 and solve for the lambda, that's exactly what you would do, you get exactly what Wien discovered about the energy intensity being the maximum at a particular wavelength. And that's actually related to the temperature. So we've already discussed how blackbody emits light, and the light characteristic frequencies depend on the temperature. Well, the other thing is you can actually look at something called the excitance of the blackbody, which is more or less the total energy it emits per second, which is a watt, per square meter. So basically, this is watts per square meter. It's how much power there is distributed over a certain surface area. Okay, and so the Stefan-Boltzmann Law, where this is the Stefan-Boltzmann constant, is that the excitance is equal to a constant times the temperature to the 4th power. Okay, so using that, you can actually solve for the temperature of the blackbody if you know sigma, and its temperature or its excitance. And so what we're going to do is take Earth as an example, and we're going to calculate what its temperature should be if it behaves as a black body. Okay, so the radiation from the sun in watts, how much energy we get per second, is and it's divided over the surface area of the Earth, which is square meters. That number happens to be 342 watts per square meter. Okay, so that's the total energy coming onto the surface of the Earth on average from the sun. Now the equator gets more light per square meter than the poles do, because the sunlight's hitting the poles and glancing off at an angle. So even though it's the same watts per square meter, you know, coming through, it gets spread over a larger area on the pole because it's kind of a glancing type of incidence. All right, now we have to account for the fact that the Earth actually reflects a lot of its light. And this is called the albedo. The more light that gets reflected, the less light that can be absorbed. And so the albedo of the Earth is about 0.3. That's to say 30% of the sunlight is reflected before it even reaches the surface. Or if it reaches the surface, it's not absorbed because it's hitting something like snow or ice. And so that means the amount of power per square meter it gets absorbed is about 70%. And so that means of this 342, the actual number is going to be 239.4 watts per square meter. And so we're going to plug this constant into here, and this for J star, and see what we get for temperature. Well, you should be able to do this yourself. And the average temperature of Earth, if it acted as a black body, that's to say if it had no atmosphere whatsoever, and this atmosphere did not also contribute to the radiation, would be 255 Kelvin. Now that's below freezing, because freezing is 273 Kelvin. And so basically the average temperature of Earth would be way below 0, actually closer to 0 Fahrenheit, which of course is in Alabama, never gets that cold here. So there's something obviously going on, and that's the greenhouse effect. Okay, so this analysis assumes that the energy is absorbed by the surface raises up to a particular temperature until the rate at which radiation leaves the surface equals the rate at which radiation comes in. But because the atmosphere absorbs the radiation going out, the infrared going out, and re-emits it coming down, the amount hitting the surface is actually greater than 342 watts per square meter, and that's the greenhouse effect. The more infrared that gets radiated back to the surface, the higher this number is, and the higher that number is, and the higher temperature that's it basically for the blackbody radiation. I'm going to ask you in class for examples of blackbody radiation and temperature and see if you kind of know, can you see the light coming from that blackbody or not?